Okay. So the title is a little bit different.
Yeah, sorry.
Abstract Schur functors.
Yeah, so my name's Joe, and I work at the National Institute of Standards and Technology, and I'm going to tell you about abstract Schur functors today. I also wanted to start with acknowledging that I did this work on occupied Kauai, Tonga, and Piscataway land. Hazelwinkle says of the representation ring of the symmetric groups, which I'm denoting as lambda, that it seems unlikely that there is any object in mathematics that's richer or more beautiful than this one. So this ring has a very rich structure, has a lot of very deep connections to many fields of mathematics. And the goal of today's talk is to uncover or shed light on this structure and its origin from a categorical perspective. So here's the outline of the talk. I'm going to tell you about some of the structure that this object has before I tell you about how we're going to categorify it. So birings and plethores, and then in order to categorify it, I have to tell you about how I'm categorifying the notion of rings. That's two rigs. And then the title of the talk, Abstract Schur functors, is going to be a very important example of a two rig. And then I'll categorify the structure into two birigs, two plethores, and then at the end, the main theorem. And hopefully I can sketch out some of the proof. Right, so by ring, I mean a commutative and unital ring. I have to get that out of the way first. But a biring is going to be a ring object in ring op. And so what that amounts to is saying that we have a ring which is equipped with these extra structures, which are ring homomorphisms representing co-addition, co-multiplication, dual versions of all the structures that a ring has, satisfying dual versions of all the laws that they obey. There are some easy examples of birings that appear. So Z is a biring, and all of the structure maps are pretty trivial, so I won't spend much time on it. But the ring of polynomials in one variable has a slightly more interesting biring structure. Here's all the formulas for it. And the thing I want you to keep in mind about this particular example and the way that I wrote down the formulas is that Z adjoint X is the free ring on one generator, and I'm explicitly using that back to define all of these structures. So it's very important that this is the free ring on one generator. I just want you to keep that in mind. So birings, what can you do with a biring structure? In general, the set of ring homomorphisms from one ring to another doesn't get to be a ring itself. If you tried to define pointwise operations on it, the sum of two ring homomorphisms won't be a ring homomorphism. It won't preserve products anymore. But if you have a biring and then any other ring, there is a ring structure you can put on this Hom set, and it's given by precomposing with these co-ring structures. So the sum of two ring homomorphisms, for instance, will be just the composite of taking first the co-addition, then doing F and G in parallel, and then doing the codiagonal, which in the case of rings is going to be just multiplication, and very similar for multiplication. And so you can define a ring structure on this Hom set, and moreover, it gives you a lift of the representable functor given by your biring to an endofunctor on the category of rings. So here's our two examples of birings that I told you about before, and here's the endofunctors on the category of rings that they represent. So since Z is initial in the category of rings, there's only one ring homomorphism into any other ring. And so the ring structure that you can give to this is always just going to be trivial ring, and it's the functor is the constant zero ring functor. Then the ring of polynomials is free on one, and so the ring homomorphisms like this are exactly the elements of the ring that you input here, and so this represents the identity functor on ring. These functors are always going to be right adjoints. It's not too hard to show, and this characterization of them as right adjoints actually characterizes them completely. So birings are exactly the same thing as right adjoints endofunctors on the category of rings. There's an op here, but that's just due to the maps being given by the precomposition, and also left adjoints if you didn't want an op there. So the category of birings is equivalent to the category of right adjoint endofunctors on the category of rings, and this is going to give us some more structure to the category of birings. So right adjoint, so endofunctors you can compose, and that gives a monoidal structure, and that continues to be true for specifically right adjoints, because right adjoints compose to give right adjoints, with their left adjoints being just the composites. And so this defines a monoidal structure on the category of birings. So on the right adjoint endofunctor side, it's just composition, and then we pull that over to give a monoidal structure on the category of birings. We call this substitution, and the unit object is polynomials because it represents the identity functor. Now with this monoidal structure, it's not symmetric, but we can take monoids with respect to that, and that gives exactly the notion of a plethory. A plethory is exactly a monoid in the category of birings with this substitution monoidal structure. Another way of thinking of it is that the lift of the representable it's always a right adjoint, but we're now asking it also to be a comonad. Sorry if there's extra noise coming from outside. Yeah, so we're asking it to be a comonad, and the co is coming from the fact that it was equivalent to right adjoints op. Another way of looking at this also is to say that it's a biring which is equipped with biring homomorphisms, going from the substitution product with itself to P, and also a unit, and it's associative integral. So for the examples, we have Z. We said before it was a biring, but it is not a plethory. And I won't tell you why. I think it's fun to figure out exactly why if you're curious, but I'll let you figure it out. But the identity functor on the category of rings is obviously going to be a comonad, and that's an easy way of explaining that the ring of polynomials is a plethory, and the plethism operation is exactly polynomial composition. So just composing polynomials like you do in elementary algebra is giving you the plethism structure on this ring. Lambda, the representation ring of the symmetric groups, is also going to be a plethory, but I haven't told you much about that, so I'm just telling you that we will see eventually that it is also a plethory. So now we can begin to categorify these notions. So a two-rig is what we're going to use as the analog of rings, and it's slightly different than what Fosco mentioned earlier in this week. It's a symmetric monoidal Cauchy-complete linear category. So we're taking vect-enriched categories and asking them to be Cauchy-complete, meaning that it has biproducts and a zero object and all idempotent split, and it's also got a tensor product and distribution of the tensor product over direct sum is automatic, since any functor preserves absolute colimits. So some examples of categories that fit this description. The category of finite dimensional vector spaces is actually the initial 2-rig. Can also take a bunch of other, there's a bunch of other categories which are famous, and I'm not going to talk about them at all, but it's good to know that there are other things that fit your definition. But there is another 2-rig that I will be talking about for the rest of the talk. So let me tell you about that. An abstract Schur functor, we're going to define it to be a pseudo-natural transformation from the forgetful functor from 2-rigs to cat to itself. So it's an endo-natural transformation of this forgetful functor. And we're going to let the category of Schur functors be, have those as objects and then modifications for its maps. So unpacking the definition a little bit, if you have a 2-rig map, meaning just a monoidal functor, between two 2-rigs, then a Schur functor has components which are just ordinary functors, but which commute with your 2-rig functor up to isomorphism. And so the reason that we call these abstract Schur functors is that if you look at the fin-vect components of any one of these, you always get what is classically known as a Schur functor, like by representation theorists. So some examples of those are like taking symmetric powers or exterior powers, or lots of interpolations between those two things. And often when you study representation theory, you often approach these things with Young diagrams and lots of combinatorics to try to even get around to defining Schur functors and the way that they interact with each other. It becomes very complicated, and it is known by representation theorists that the composite of two Schur functors is a Schur functor, but the way that it's presented with Young diagrams is confusing and is an open problem in general. And this is known as the plethism problem. That really is the origin of this name, plethory, that's throughout this talk. That's just a little bit of history about this. So here's the first main theorem of this paper is that the category of Schur functors is the free 2-rig on 1. So here's a sketch of that fact. I don't know why it only says SK. That was supposed to say sketch. The forgetful functor from 2-rigs to cat is represented by the free 2-rig on 1. This is an analog to a calculation you can usually do with set right here. But the functor that's represented by the free 2-rig on 1 is the same thing as the functor which is mapping from the functors from 1 into the underlying category of a 2-rig. But this is the same thing as saying pick out the objects of the underlying category and then also morphisms. So it's just giving you the underlying category. So this forgetful functor is represented by this, whatever the free 2-rig on 1 is. But now with this in hand, we can do this calculation and say, sure, we defined it to be this category of natural transformations and modifications between them. But we just said that that's represented by F1. And so we just replace that here. But now the 2-dimensional version of the Yoneda lemma is going to tell us that we can actually just look at maps between F1 and itself. But then again, this is the representable functor being applied to F of 1. And so we can apply our above observation again and end up with just the underlying category of the free 2-rig on 1. So the category of Schur functors is the underlying category of the free 2-rig on 1. Right, so now we have a notion of categorification of rings, and what I claim is a really important example of those, the free 2-rig on 1. we can begin to categorify birings and plethores. So a 2 birig, we're going to define it to be a 2 rig, which has a lift, is equipped with a lift of its representable functor. So we're gonna skip the sort of writing down cooperations sort of definition and go straight to the this other characterization of birings and say that it has a lift of its representable functor. And this is what we're going to take as the definition. And we can also use the other characterization of plethores to define our categorification of it. So a 2 plethore is just going to be a 2 birig, which is also equipped with a structure of being a comonad. So this is all in parallel to the characterizations that we had of the structure of a biring and a plethore. And we also get similar examples of these things. So the initial ring is Z, and we also have that the initial 2 rig is on dimensional vector spaces, and this gives a 2 birig, and it represents the constant 0 2 functor. And similarly, it's also not a 2 plethore for like the exact same reasons. And then just as polynomials on one variable was the ring on one generator, the 2 rig on the free 2 rig on one generator is Schur, and that's going to be a 2 plethore, in fact, and it represents the identity 2 functor. So everything is happening exactly as it did in the ring world. And the identity 2 functor is a comonad, and so that's saying that Schur is a 2 plethore. And now here's our main theorem. The second main theorem of our paper says that this 2 plethore structure on the category of Schur functors induces the plethore structure on the ring of symmetric functions, or the representation ring of the symmetric groups. So I'm going to have to skip telling you why lambda happens to be the Grothendieck group of the category of Schur functors. I could tell you late after the talk if you want. But now I'm going to attempt to sketch some of the ideas that go into proving this main theorem. So first I'm going to break taking the Grothendieck group or the Grothendieck ring into 2 steps. First is taking isomorphism classes, and then second is tensoring with Z to turn a rig into a ring. And so now here's an analog of the main theorem that only looks at the first step, the 2 plethore structure on the category of Schur functors is now inducing the rig plethore structure on. So this is just saying everything I said before about what a biring and a plethore are, just do it for rigs instead of rings, and then we get the plethore structure on the isomorphism classes of this from the 2 plethore structure on the category of Schur functors. So now I'll begin telling you why this is true. So we already have that taking isomorphism classes is going to be a ring. That's not too surprising, but taking isomorphism classes does not preserve coproducts of 2 rigs in general. That would make it really easy to say that we get a birig automatically, but it does happen to preserve these coproducts in particular, these tensor products of the free 2 rig on 1. And actually proving that requires delving into some representation theory, and so I'll skip it for the sake of this talk, but we do get an isomorphism here. And so we actually do get by ring structure or by rig structure on this pretty easily. Now I'm going to claim that taking isomorphism classes of a category is going to be the same as looking at maps from one into your category. In this category, which I put a subscript H, I mean that I'm taking the two categories and taking isomorphism classes of the one cells to make this a one category. When you do that, taking isomorphism classes is exactly the same as mapping out of one. Then we can lift that up to looking at two rigs and say that taking isomorphism classes of your two rig is the same as looking at two rig maps from Schur into R, but similarly in this one category where we took isomorphism classes of the one cells. And then now if we take R specifically to be Schur, then we get lambda plus here is this isomorphism classes of that category is going to be two rig maps from Schur into itself. But then we can apply the functor J to like on the Hamset level and get a map into J of Schur, rig maps from J of Schur to J of Schur, which is lambda plus to lambda plus. Now with this sort of map, going from lambda plus into maps endomorphisms of it, we can actually rewrite that as saying that it's a map from lambda plus into its own lift of its representable functor applied to itself. And when you have something like this, the Unedo lemma is going to tell you that you can have it. It's analogous to specifying a morphism, a natural transformation between these two functors, and sorry, and then sorry. And then you get a natural transformation of this form, and that gives you exactly the comonad structure. I'm sorry, I lost my words for a moment. And that's it. That is the amount of detail I'm going to go into right now and have the time to go into right now. But this gives you the comonad structure that makes it into a plethora. And now there's sirens coming, so I'm going to try to mute.
I'm afraid we don't hear you anymore. So, are there some questions? No questions?
Okay, sorry. I wanted to mute myself because there was an ambulance coming and there was lots of sirens, but then I couldn't unmute myself after that. Yeah, so sorry, I'm done. Here's a picture of a coop.
Fine.
Yeah, just in the definition of a two rig,
yeah,
you asked for idempotent split, I think.
Yeah.
And I was just wondering what value you get from that.
Yeah, so an important reason that we ask for idempotence to split is that if you look at sort of the nitty-gritty details of defining Schur functors, or of like the classical way that you look at defining Schur functors, one of the steps in that is that you're going to have an idempotent map, and you want to look at the image of that map, and that's going to be in certain cases that gives you exactly the irreducible representations of a symmetric group, and that's like that's how representation theorists define a Schur functor, because they want to talk about representations of they want to talk about the irreducible representations of a symmetric group, and you get it from taking a certain vector space and then a certain endomorphism of that, and then looking at the image and saying that's you have to prove it, but you get that that's the irreducible representations. And so what we're doing here is saying you can actually do exactly these operations, all these constructions on a category that has a certain structure. One of the structures that you need is the ability to split an idempotent so that you can like take its image. And so really what we're asking for here is for categories to have exactly the structure you need to perform the construction of Schur functors in the classical setting on vector spaces, but on just whatever these other categories are. So that's why we specifically are asking for these colimits.
Okay, that makes sense. Thank you.
Okay, anybody else?
Thanks for the nice talk, Joe. I can't help but notice that the n goes missing when you go up to 2. And I wonder, I mean, the story seems very closely analogous, except that towards the end, the proofs get a bit fiddly when you want to show that the two-Plättery structure induces the Plättery structure that you were looking for.
Mhm.
But is that basically saying that in the ring case, having the ability to having negatives is not really relevant to this structure, or is there, I don't know, there's an obvious difference between these, and I'm wondering how it affects your theory.
So something that I've left out completely is that to actually completely prove the main theorem, we have to look at this other side too. I only talked about the first step, constructing a rig. Actually, like group completing and having the structure come along all the way to the ring is pretty involved. It requires a lot more work, much more than I could fit in this time frame. So I think well, maybe you're asking about why at the categorified level there's not really a need for expressing the negatives. I think there is, in a sense. We don't in the definition of Schur that I gave you, because that's really what's happening when you look at the things that representation theorists care about, Schur functors and stuff. There's no subtraction in these contexts. But to actually go through with the entire proof of this, we do also come up with a thing which has something like negatives. So we have we have what are called Z2 graded Schur functors, and that's what we're using as the thing which is like the category of Schur functors but has negatives, and that's a critical ingredient in the full proof that the two Plättery structure descends to the Plättery structure on the ring.
Great.
So there is something at the categorified level.
Okay, I think we have to conclude here. Let's thank the speaker again. And we have a break of 2 minutes.